Okay, guys, thanks for taking the time to watch this lecture since I'm out of town. I appreciate you uh, either sitting down during the time lecture is taking place or another time to look at this. But we'll be covering in this lecture a little bit about high pass and band pass filters that are relevant to lab number 3, the two types of filters that we didn't cover in the last lecture. But before we get into the details there, I do want to do a brief review of what we talked about last week because concepts of the low pass filter are going to play a role. Convolution, frequency and time domain will come into play when we're discussing high pass and band pass filters. So very broadly, remember that filters are a way to remove unwanted components of your signal based on their frequency. That's what we're focusing on here in electronic circuits used as filters. And to understand how your filters are modifying your signal, what we want to figure out is the instrument response function, how our filter is responding in time, which we're calling the IRF, or in the frequency domain, the frequency response function, which we're using this phi omega to represent. So this is a way to quantify how your filter is going to be modifying your input signal, S of t, and modifying it to get your resulting output signal, or O of t. So we drew this on the board last week of a visual representation of what we mean by our signal in, our instrument response function, or that would be our filter here, and then our output signal. So how do we quantify, how do we determine our instrument response function? And then we also want to remember that the relationship between the instrument response function and the frequency response function is that they are a Fourier pair, this arrow representing the Fourier transform. We can then move between the time and frequency domain with that Fourier transform, which is important. So mathematically, how we determine this output signal based on our instrument response function and our input signal is by taking a convolution, where remember this asterisk symbol here represents a convolution. And mathematically, how we write out what a convolution is actually doing is that if you have a function, a given function 1, f of 1, and a given function f of 2. In the time domain, what you're doing when you're taking a convolution is you're multiplying these two functions together as they're being shifted. One is being shifted relative to another with this pseudo time variable t prime. And so you're multiplying those together and then integrating the area underneath the curve after that multiplication. So I tried to draw this on the board last week, but here's one of those animations that I did want to mention, where here we have this step with an exponential decay being convolved with a square wave pulse. So you can see that as they begin to overlap, we can look at that area under the curve. So this is also getting at Kate's question last week, where here, once it passes that peak, if one signal is higher than the other signal, that area doesn't contribute. It's just the area where they overlap. So you can see that the black line here is then the convolution of those two signals. So the resulting convolution between this square pulse and this decay is that we're broadening. It follows the exponential decay later on, but we also have this slope, so we no longer have a step function here, which is very similar to what we drew on the board last week of that Gaussian spreading out the step function as well. So that's all in the time domain, and doing convolution in the time domain is a little bit more difficult. That at the end of the lecture last week we talked about that if you do a convolution in the frequency in the time domain, it's equivalent to the Fourier transform of taking the product of those two signals in the frequency domain. Because of this, it's a lot easier to take a product as opposed to doing the convolution where it's a product and an integral, that oftentimes it's much easier to characterize the frequency response function and how it's modifying your signal to get the output signal in the frequency domain, and then just performing the Fourier transform to get it into the time domain. So that's why with the low-pass filter we talked about the frequency response function first before talking about the instrument response function. Also, thanks for the updates, Windows. We talked about the low pass filter, and just a quick recap that it was an RC circuit where we have our resistor here and the capacitor here, and that we went over quantitatively what the instrument response function, this is the frequency response function here, and that we characterize this frequency response function with a cutoff frequency, where we see at the cutoff frequency that our voltage changes by 1 over the square root of 2, or 3 decibels. Remember that we were plotting on those log scales and to get comfortable with decibels. We can then, this frequency response function takes the form of a Lorentzian. So make sure when you're looking in the frequency domain that you don't mischaracterize your frequency response function as the wrong shape. It is 1/2 of the positive half, since we're only looking at positive frequencies, the positive half of a Lorentzian. So then, since the frequency response function and the instrument response function are Fourier transforms one another, the Fourier transform of a Lorentzian is then an exponential. So we can then, in the time domain, our instrument response function is an exponential decay with a time constant that's inversely related to our frequency cutoff. And then finally, we also went over the phase shift equation as well. So that's a quick recap of our lecture from last week. So let's get into the new material of looking at the high pass filter. And you can see with the high pass filter, the circuit diagram is shown here, where again, it's an RC circuit, but if you go back a couple seconds to the previous slide, you'll see that the capacitor and the resistor are switched here. So when we're characterizing a high pass filter, it is very related to what's going on with the low pass filter, because it's just the switching of that RC, the location of the capacitor and the resistor. So the response is just flipping the low pass filter. So if we characterize how our output voltage looks for a high pass filter, we can just characterize it as our input voltage minus the behavior of a low pass filter, that they're inversely related. So if we want to write our frequency response function out, we just go to the equations from last week, and then we subtract that from a constant. So here, this is our frequency response function. Again, to remove imaginary components, I'm taking the square here, or taking the value times its complex conjugate, so we don't have to deal with imaginary components. Where you can see that this is our response from our low pass filter, and we just subtract that from our input voltage, where 1 here is just a constant representing our input voltage. Just this is a constant value here. So it's not necessarily 1, it's going to vary based on what signal you're inputting, but realize that we have this subtraction from the low pass filter. So this is how we can represent it with the frequency response function here. So if we want to then plot what our frequency response function looks like on a graph, on a linear scale, we see the shape that it again has that Lorentzian type shape, since this is a Lorentzian here, that it's just flipped, that we have the characteristic curvature at this lower frequency. You can see that the output is very low then, and then we have this decay that's characteristic of a Lorentzian. It's not an exponential. Just want to repeatedly emphasize that this is not an exponential rise. This is a Lorentzian because of this curvature here. But we see that the output at high frequencies, we do see that those high frequencies can pass through, and at the low frequencies, they're cut off, where you can see if we have a high value here, this term goes to 0. So our voltage out scales to our voltage in at very high frequencies. While very low frequencies, this denominator is going to be close to very small. This will be 1 minus 1, and then this will decrease according to the lower frequency. If we put this on a log scale, remembering what we mean by decibels, here we see that again it's just a flip of the low pass filter, where we have the same characteristic cutoff frequency and slopes that on this log scale that we saw for the low pass filter. And if we write out what this cutoff frequency is, or the time constant in the time domain, we have the same exact values as the low pass filter. So you need to know where the capacitor and resistor are relative to one another So you can say which direction, if it's the high frequency being cut off at that omega C, or if it's the low frequencies being cut off based on the locations of those circuit elements. So commit that to memory, that for the high pass filter, the capacitor comes first, the resistor second. Think about how capacitors perform electronically to try to remember that, because I'll guarantee you that once we get to the quiz and there's going to have to be a sketch of either the high pass filter or the low pass filter, some of you guys are going to switch those. So try not to be one of those people, remembering if it's the C first or the R first. So if we look at the high pass filter in the time domain, again, remembering that we have in the frequency domain, it's just a constant minus the low pass filter response where this 1 represents a constant. If we want to think about if we're taking the Fourier transform where we have a constant present, what is the Fourier transform of a constant? So try to recall from Lab 2, also the second lecture we had on Fourier transforms, that the Fourier transform of a constant is a delta function. So if we take this, the Fourier transform of our frequency response function for a high pass filter, what we're going to see is that there's a delta function present here, and then we have the Lorentzian aspect, this low pass filter here. The Fourier transform of Lorentzian is an exponential. So this is showing that all the frequencies pass through at this lower band here. So it's best to think about this instrument response function in time as convolving the signal of a delta function and an exponential decay. So you can think about the high pass filter in these two separate components. So short times are high frequencies, so that's why we see this high delta function component here. And then finally, with the high pass filter, it's also useful to look at the phase response as well, since that will be some questions in Lab 3. And again, we're just seeing that it's the inverse of a low pass filter, where if you remember the low pass filter, this fraction here was flipped. So if we plot this, the phase versus the log of the frequency, we see at the cutoff frequency, we have a shift of 45 degrees. And it's 90 at low frequencies and 0 at high frequencies. So at high frequencies with the high pass filter, we want it not to be modified, the signal to be minimally modified, so that's why this goes to 0 here. Okay. So switching gears to the band pass filter. Again, I encourage you guys to go look at your Phys 122 labs that are online. That for the band pass filter, we have an LCR circuit where we have, in this sketch here, we have the inductor in series with the capacitor. And when these are shown in series, the capacitor is playing the role of blocking the low frequencies, while the inductor blocks the high frequencies. Frequencies that are in resonance with both the inductor and the capacitor are then allowed to pass to our output voltage. This is how this bandpass filter works when these are in series. It performs differently when they're in parallel. So take a look at, again, those Phys 122 notes, where here we show that what we mean by bandpass, that low frequencies are cut off, high frequencies are cut off, and a certain band passes through. And where this band falls and how wide this band is depends on the electronic component you select. So this band is centered on this omega naught here, where that is inversely related to the square root of the inductor and capacitance. So that's where it's centered at. And then the width of the band is characterized by something we call a quality factor here. So that is where the resistor comes into play. That the center value is this omega naught, the width, the full width half max, is going to be this delta omega, and you can characterize this quality factor by taking the square root of the inductance divided by the capacitance and dividing that all by the resistance. So you'll be characterizing and quantifying this in lab number 3, and also this is just one of the important values of what frequencies your bandpass filter cuts off. So that's always going to be a value that's important when you're using a bandpass filter. We can also look at the frequency response. We're not going to go through the whole derivation. This is in the Phys 122 manual. That recall that the frequency response is this equation here, where we have the resistance, the frequencies, the inductance, and the capacitance, where you can see when that frequency is in resonance based on L and C here, it's able to pass through. And if we plot this on a linear scale, we get a plot that looks like this. Note that this is not a Lorentzian. A Lorentzian does not have this steep drop off on the left over here. But the way that we can think about what this frequency response is it resembles a convolution of the frequency response function of the high pass filter and the low pass filter, where it would be a convolution of the decays of the Lorentzian and the low pass and high pass filter, but also that delta function that contributes that we just saw in the plot at low frequencies of the high pass filter. So this doesn't have, we can't say that this is a given shape, a given function with a name here. So don't get confused that this is it's not a Lorentzian, it's not an exponential decay, it's its own function shown here for the frequency response function. If we take a look in the time domain, if we want to look at the instrument response function, again, I want you to think about working in your lab in Phys 122 of how you guys characterized your LCR circuits, that these are damped oscillators where the capacitor serves as the role of a spring if we're thinking to classical mechanics. The inductor is acting as a mass and the resistor is acting as a damping element. So if we look at the instrument response function in the time domain, we would see something similar to this, an exponential damping of a sinusoidal vibrations, where you can see that damping here and the sinusoidal here. And you can think about how this instrument response function would act to allow mid-range frequencies pass, but also cut off the high and low pass filters. That you should be able to make the connection of this instrument response function to the frequency response function here. And then finally, the phase response of a bandpass filter is the following equation, where you can see that at the center of our band, at this omega naught, where you want your signal to not be modified, you have zero phase shift, but at high frequencies and low frequencies, you get to 90-degree shifts. So the plot of this phase response, where we have some text that's cut off here, where the x-axis is frequency, the y-axis is phase. You can see at that cutoff frequency shown here, we have zero shift, and then we have this characteristic arctangent shape. So that's most of what I wanted to cover today. Now you guys have some equations that can help you out when working with the high pass filter and the band pass filter. I think the big takeaway is, one, that the high pass filter is just a constant minus the low pass filter. So trying to remember and keeping straight where the capacitor and resistor are, which filter lets high versus low through. And then that the bandpass filter is a convolution between the frequency response of the low pass and high pass filter in this plot here. And that to characterize a bandpass filter, you have to say where it's centered at and the width based on this quality factor here. So I hope this helps you guys with lab number 3. And if you have questions, please bug me on Tuesday once we're back in the lab or stop by my office hours.